Physics Chapter 3, Refraction at Plane Surface, Part 3. This is simple application of refraction of light. So here we are going to study about real and apparent depth. Now, an object, an object which is placed in denser medium, when viewed from a rarer medium, appears to be at a depth which is lesser than its real depth. This is because of refraction of light. For example, in this figure which you see in front of you, there is an object which is placed at a depth uh, or a point O. So this depth which you see over here is the real depth of this object from the surface till where the object is kept. This is the real depth. Okay. Now, when this object which is kept inside water or inside glass, or you can say inside any denser medium, is viewed from a rarer medium. Now you have to view this object from air or from outside water or outside glass. What happens? The ray of light which is coming from the object towards your eye suffers refraction. Now, for clarity and for clear understanding, there are many rays of light which are, getting emitted from object O, but we will consider only two rays of light for clarity. So, one ray of light goes normal, okay, and strikes perpendicular to the surface separating two media. So, when it goes normal, it does not suffer any refraction. Its speed might change, its speed might increase when it uh, travels from denser medium to rarer medium, but it will not bend because it is incident normally. So a ray of light is incident normally from the object onto the surface separating two media, and without suffering any refraction it emerges out into the rarer medium, that is air. So that ray of light is, you can say IA, and then it becomes AA dash. IA is incident ray, AA dash is refracted ray, which is actually not refracted. Okay, let us consider one more ray of light, which is basically reaching the eye, because you are viewing this object from not exactly like from vertical, you're viewing it from little bit, you can say in a slant position. So ray of light which is reaching your eye after refraction is OB, the incident ray, and BC, that is the refracted ray. So angle OBN dash, okay, at B, what we have drawn is, we have drawn a normal NN dash. So OBN dash is the angle of incidence. OBN dash is the angle of incidence. And NBC is the angle of refraction. Now, as you can see, when the ray of light enters from denser medium to rarer medium, it bends away from the normal. So here, the angle of incidence is smaller than the angle of refraction. Yeah, there is no problem with that. Okay, so this is what is happening. But what about this application of refraction? That is, what about the apparent position of the object which is inside the denser medium? For getting that, what you need to do is you need to produce this refracted ray BC inside the denser medium. Okay, so you produce this BC backward inside the denser medium, and this BC produced backward meets ray OA at position I, and this is the position of the image. This is where the object appears to be. So AI is the apparent depth. AI is the apparent depth. So this is not a very unusual phenomenon. This happens in, very perfectly in the day-to-day life. You can do an experiment at your home. You can take a vessel, put a coin inside the vessel and move little bit far away from that vessel so that you cannot see that coin. The coin hides behind the you can say wall of the vessel. Put it in the center but just move behind so that you can't see the coin. Now pour water into the vessel and stand in the same position. You will miraculously see that the coin reappears. Now there is no miracle in this. It's only thing that the ray of light which is reaching your eye, it is bent now. It was reaching your eye when water was not there. It was reaching your eye. It was not able to reach your eye because there was the you can say wall of the container in its path. But now since you have moved backwards and you have poured water into the container, the ray which was being blocked by the wall of the container is now getting bent and reaching you with the help of refraction. So the coin appears to be raised from its position. So this is not only about the coin. Any object, or you can say any uh, object which is submerged, any object which is submerged in a denser medium or put inside a denser medium, it appears to be refracted, or it appears to be have shifted when viewed from a rarer medium. So this is not only about the coin. Even if you put a pencil, it appears to be bent at the surface separating two media. If you put a pencil inside water and if you see from outside in a glass, uh, in a container made of glass, okay. Also, the depth of swimming pool, it appears shallow. This is all due to refraction. The bottom of the swimming pool, it appears to be have raised, that is due to refraction. So the depth of any object which is kept in a denser medium when viewed from rarer medium appears to be have become less. That is, the apparent depth always appears to be less than the real depth. So this process is known as the shift in the real depth, right? And that is due to refraction. Okay. So there is this derivation which I'm going to explain you very slowly, because see, this derivation, first of all, it's not part of your, you don't have derivations, you don't have this in your syllabus. Even if it is, like, if there is no syllabus cut, you don't have derivations to be asked in the exams. But still, you should, as I told you earlier, you should know how things work. You should know how things are derived in order to answer the questions in a more confident way. Okay, so let's understand what they are trying to say, and I'll keep it short. I'll keep it short. Okay, in figure 4.36, for the incident ray OB, angle of incident is angle OBN dash. Yes, it is angle of incidence OBN dash. And the angle of refraction is CBN. Yes, absolutely. Since AO and BN dash are parallel, AO and BN dash are parallel. Yes, absolutely, they are parallel. You know why they are parallel? Because this ray is believed to be normal or incident normally to the surface separating two media, and N dash is normal itself. So they both are making 90-degree with the surface. And that means they both are parallel to each other. So angle OBN dash is equal to angle AOB. OBN dash is equal to angle AOB. Okay, so if angle OBN dash is I, angle AOB is also I. Why is it I? Can you tell me why is it I? It is I because it's a, what is it? alternate interior angle. Angle AOB is alternate interior angle with angle OBN dash, and that's why they are equal. Okay. So angle AOB is equal to OBN dash. Similarly, IA dash and BN are parallel. IA dash and BN are parallel. Okay, so they are talking about AA dash and BN. Okay, so what, or IA dash and BN. Okay, IA dash. Okay, not OA dash. IA dash. Why they are saying is because if you consider IA dash, the line from I to A dash, and if you consider NN dash to be two parallel lines, this IB serves as a transversal. IB. Do you see IB? It serves as a transversal. So if this angle NBC is R, angle of refraction, angle AIB also becomes R. You know why? Because they are corresponding angles, like how we proved angle AOB is equal to angle OBN dash, alternate interior angle. In a similar manner, angle NBC is equal to angle AIB. Okay, so we have angle AIB is equal to R because it is equal to angle NBC, corresponding angles, and we have angle AOB. AOB is equal to angle I, which is equal to angle OBN dash, alternate interior angles. Okay, itna clear hai? Now look at the right angle triangle BAO. Can you see right angle triangle BAO? If you cannot see, I will highlight it for you. Let me erase everything here. Now focus on right angle triangle BAO. Okay, can you see right angle triangle BAO? This is the right angle. Okay, so in this right angle triangle BAO, they are saying that sine I. Do you see this angle I? Sine of this angle, sine I. Now what is sine I equal to? You remember SOHCAHTOA? SOHCAHTOA. So means sine, that is equal to opposite upon hypotenuse. Sine I is equal to opposite upon hypotenuse. Now what is opposite of angle I? AB. And what is hypotenuse? Hypotenuse is OB. Sine I is AB upon OB. Let's check. Correct. And in right angle triangle IAB, can you see triangle IAB? And can you see what is sine R equal to? Sine R is also equal to opposite upon hypotenuse, and opposite of R again is AB, and hypotenuse is IB. AB upon IB. So sine I's value we have got and sine R's value we have got. Sine R is AB upon IB. Okay, but the definition of refractive index tells us that the refractive index of air with respect to a medium, the refractive index of second medium with respect to the first medium. Second medium is air over here, and the first medium is water. That is, let's write M. Okay, the refractive index of air with respect to a medium is equal to sine I upon sine R. We know the values of sine I and sine R. Sine I is AB upon OB, and sine R is AB upon IB. Okay, OB comes down, IB goes up. So this will become, see, AB will get cancelled right away, and this will become IB upon OB. IB upon OB. IB upon OB. Okay, so we have got sine I upon sine R as IB upon OB, which is equal to refractive index of air with respect to the medium. But what is the refractive index of medium with respect to air? It is 1 upon the refractive index of air with respect to medium, which is OB upon IB, reciprocal of the earlier fraction which we had got. Since the point B is very close to the point A, that is, the object is viewed from point vertically above the object O, IB is equal to IA. So there is one you can say assumption which they have made, that IB is equal to IA or OB is equal to OA. Since these 2 points A and B are not very far away, that's why this assumption they had taken earlier. In this you can say box, they have written this assumption that IB is equal to IA and OB is equal to OA. So if IB is equal to IA and OB is equal to OA, we can say that we can replace OB here with OA. What is OA? OA is actually the real depth. And what is IA? IA is apparent depth. So refractive index of a medium with respect to air, or absolute refractive index of any medium, is equal to real depth upon apparent depth. So this is the formula which we have derived. And from this formula, we can also say that apparent depth is equal to real depth upon absolute refractive index of the denser medium. Okay, so this is how you derive this formula for apparent depth. So what is shift? See, shift is OI. If I erase this whole thing, I can get the formula for shift. Shift is nothing but the real depth minus the apparent depth. So shift is real depth minus apparent depth, which is basically apparent depth formula. If you put in apparent depth formula, is real depth upon the refractive index of the denser medium. Okay, so if you put the formula in apparent depth and take out real depth common, you get shift as real depth multiplied by 1 minus 1 upon refractive index of the medium. Okay, now the shift by which object appears to be raised depends on, number 1, refractive index of the medium, number 2, thickness of the denser medium, and number 3, color or wavelength of incident light. Okay, the shift by which the object appears to be raised depends on the refractive index of the medium, the thickness of the denser medium, and the color or wavelength of incident light. How does it depend? Now, refractive index. Greater the refractive index, more is the shift. Higher the refractive index, greater will be the shift. So if the denser medium has the greater refractive index, the shift will be greater. Okay, what about the thickness of medium? Thicker the medium, more is the shift. More thick the medium is, shift will be higher. That is, if the depth of a swimming pool is very large, okay, it's a deep end, then it will appear more shallow. It will appear more shallow than the shallower end. Okay, so shift increases on increasing the depth or the thickness of the medium, and dependence on the wavelength of color of light. See, for violet light, the refractive index of any medium is greater than for red light. So that means for light of shorter wavelength, the shift will be higher. So shift will be higher for violet light and shift will be lesser for red light in a given medium. Okay, let's take examples. For glass, the absolute refractive index of glass is 3 by 2. So thickness of glass slab appears only 2/3 of its real thickness. How come? Because we know that apparent depth is real depth upon the refractive index. So if you say a glass slab has thickness of x mm. Okay, a glass slab has thickness of x mm. So what will be the apparent thickness? Okay, apparent thickness या फिर apparent depth or thickness is equal to real depth upon absolute refractive index of glass with respect to air. So apparent depth will be, real depth is x upon the absolute refractive index of glass is 3 by 2. So this will become 2x by 3. So the apparent depth will be 2/3 of the original depth. That's what they are saying over here. The glass slab appears only 2/3 of its real thickness, right? For water, the absolute refractive index is 4 by 3. So depth of water pond appears 3/4 of its real depth when seeing from air in a nearly vertical direction. That is, it appears shallow. So let's say that a swimming pool has a depth of swimming pool is 8 feet. 8 feet. Okay. So what is the apparent depth? If somebody watches this 8 feet depth swimming pool from little far away, how will it look like? How will it appear? How deep will it appear? So apparent depth of swimming pool is equal to 8 feet upon the absolute refractive index of water, which is 4 by 3. So 8 multiplied by 3 upon 4. So it will appear to be of 6 feet. It will appear to be of 6 feet. Okay, and then if a person jumps in, he'll find out that if a person is, you can say, 6 feet tall, he will find out that the water is 2 feet above his head after jumping in, because the apparent depth seemed 6 feet. Okay, so this is why a fish, when seen from air, appears to be nearer the surface of water than its actual depth. The apparent depth of an object lying in a denser medium is always less than the real depth when viewed from any direction in the rarer medium. But the above equations, 4.13, which one is? Yeah, these equations they are talking about are valid only when the object is seen from vertically above. Vertically above means you are not looking at the object at a very much slant position. You are looking at the object from vertically above. Okay, so that is, you can say, it is considered when we have this such a simple formula, and when we consider IB is equal to IA and OB is equal to OA, it is to be considered that we are looking at an object from vertically above. Anyways, next is apparent bending of a stick underwater. So this diagram you must practice for your exam. So how to draw this diagram? See, what you do is you draw a stick, half of it in air, half of it in water or denser medium. You draw I in the rarer medium, that is air. Now you draw two rays of light coming from the stick, okay, in onto the boundary of uh, the boundary separating two media. So at these 2 points, these rays of light will be incident coming from the stick. Now at these 2 points you might want to draw normals. That will give you more clarity. So what will happen is these rays of light will bend away from the normal. You have to show that they bend away from the normal, like how it is shown over here. Now these refracted rays of light will reach the eye, but where are they coming from? That is also important. So these refracted rays are produced backward into the denser medium, and they meet at point P dash, which is exactly above P. So this P dash is the point where the end of the stick appears to be when viewed from outside. So if we join this end P dash with this point O, what happens is the stick appears to be bent. It is not bending, it appears to be bent. Okay, so this is the actual stick, and this is the bent part of the stick. So this is how it looks like. Thus part PO of the stick or pencil appears to be P dash O. The immersed part of the stick appears to be raised and therefore bent at the point O on the surface of water, and the stick or pencil appears to be as XOP dash. An object placed in rarer medium when viewed from a denser medium appears to be at a greater distance than its real distance. Okay. Now, I'm going to talk about something really interesting over here. If you have tried underwater swimming, I don't know how many of you know swimming and how many of you are able to actually go underwater and see outside. But if you have tried, then you will see one very amazing thing. Suppose your friend is standing outside the pool, outside the swimming pool, and you are viewing your friend from under the water. Now, when you look at the face of your friend from under the water, he appears to be a little far away than actually he is. He is nearer to the water, to the swimming pool, to the surface of water, but he appears a little far away, and that is also due to refraction. So an object, when viewed from a denser medium, and when that object is placed in a rarer medium and it is viewed from a denser medium, appears to be at a greater distance than its real distance. Okay, see, this is how it happens. This is an object in rarer medium viewed from a denser medium. Great. This is exactly opposite of the first diagram which we saw over here. Okay, some consequences of refraction of light. In our daily life, we come across many phenomena which are caused by refraction of light. Some of these are given below. A star appears twinkling in the sky due to change in the refractive index of air with temperature. Why does stars twinkle? See, the light coming from a star is coming from very huge distance. It's coming from very far away. So far away that star, although being larger than the sun, than our sun, being so far away, the light coming from it appears to be coming from a point source. So it comes like a ray of light. And this ray of light, when enters our atmosphere, it undergoes multiple refractions due to change in the refractive index of air with temperature. You know, there are different layers of air or atmosphere, and all these layers, all these you can say uh, uh, different thicknesses or different altitudes of atmosphere have different temperatures. Due to these different temperatures, the refractive index of those particular thicknesses or those particular mediums will also change, and due to that change in the refractive index, what will happen? The ray of light which is coming from that distant star, this distant star will appear to be bending, will appear to be have bent. So a ray of light coming from a star passes through all these different layers of atmospheres which have different temperature, and because of that different refractive index. And these rays of this ray of light coming from the distant star continuously bends from one place to other, from other place to the first, and that's why when you see a star, it appears twinkling. Then the sun is seen a few minutes before it rises above the horizon in the morning, while in the evening a few minutes longer after it sets. I will show you a diagram for this, and then I will explain you this consequences of refraction. Okay, so in this figure you see sun with its true position below horizon. You see this line? This line is horizon. You know what is horizon? So horizon is that imaginary line where you see the sky and the earth meeting when you look very far away. Okay, so uh, when you look at horizon and when the sun is setting or rising up, suppose the sun is above horizon. Now actually the sun's position, the true position of sun is this. This is the true position of sun, but it appears to be above the horizon, right? If the sun has not risen still, it appears to have already risen. If the sun has not set, if the sun has already set, then the sun appears to be above the horizon and about to be set. So why does this happen? Because the rays of light coming from sun, they suffer refraction throughout the layers of atmosphere. Now you see atmosphere over here. From this point up to this point there is a huge thick layer of atmosphere, and in every layer the you can say the rays of light coming from sun goes on suffering refraction and reaches you in such a way that the sun appears above the horizon before it has risen, and appears above horizon after it has already set. So this is you can say the pictorial representation of sunrise and sunset, which is you know a phenomena due to refraction in atmosphere. A coin kept in a vessel and not visible when seen from just below the edge of the vessel can be viewed from the same position when water is poured into the vessel, which is the experiment which I told you to do. You can try it yourself. A print appears to be raised when a glass slab is placed over it. Okay, so this also I can show you with the help of figure. Print under glass slab. Okay, print under glass slab. I don't know. Maybe letters raised under glass slab. Hmm. Okay, I don't find any pictures for that. So what happens is, you might have seen in many offices they keep a glass slab on the top of the table, and under that glass slab it's a thick transparent glass slab, and under that table they keep many important documents, some important, not documents as such, but some important contacts, some visiting cards, or some some important information. And this information, or the printed letters or the printed matter on that paper, appears to be raised when viewed from an angle. That is also due to refraction. Then piece of paper stuck at the bottom of glass slab appears to be raised when seen from above, the same thing. Then a tank appears shallow than its original or actual depth, that is same with swimming pool. And a person's legs appears to be short when standing in a tank or a swimming pool. So these all are the consequences of refraction of light in our atmosphere. So just go through the examples before doing this exercise, and there are some interesting solved examples, very easy. The formula which we have derived, which I have discussed with you in detail, are to be used with these numericals. And then there is exercise 4C. I want you to complete this exercise, very small exercise, so you can finish it in one day. And then we'll go to this next part, that is critical angle and total internal reflection. So this video will be out very soon, and this is a very important concept, very you can say a useful concept, which we will go through. So this was a huge chapter. After this, the two chapters of light are not very big. uh, the next chapter is about lenses, refraction through lenses, which has ray diagrams and some numericals. So that could be understood uh, without much delay. And then after that, there is the next chapter is about you can say the electromagnetic spectrum, which is also very interesting, very small chapter, not very lengthy. So please do the exercise 4C, and I'll be out with the next video very soon. Okay, see you very soon. Bye bye.